All right, the last example of 16.3 is, oops, let's go back there, is a very interesting example. And it's a little bit more of a investigation into the theory, into some of the more subtleties. So I enjoy this. So this problem asks us to show that this vector field, they call it the vortex field because if you were to graph it, it kind of swirls about the origin, satisfies the cross partials condition, but is not conservative. And then they ask us a follow-up question whether or not it contradicts theorem 3. So let's go ahead and start by calculating or showing that the cross partials condition is satisfied. And since some of you might not know what this is referring to, this right here, cross partials condition, i.e. del f2 del x equals del f1 del y are equal. That's what it's referring to. So let's go ahead and take those partial derivatives and see what we get. So del f2 del x, this is taking the x partial of x over x squared plus y squared. We'll go ahead and use the quotient rule here. Actually, I guess I'll just make this a line outward. So the quotient rule says derivative of the top, which is 1, times the bottom left alone. So 1 times that is that, minus the top times the derivative of the bottom. And the derivative of the bottom with respect to x is 2x. And all over x squared plus y squared, quantity squared. So this should be, when we do this, collecting like terms, this should be y squared minus x squared over x squared plus y squared, quantity squared. Right, because this is a x squared, and then this is minus 2x squared, so that's negative x squared, and then we still have that positive. So I just switched the order because I think that looks a little bit nicer. Okay. For the next one, del f1 del y. So this is the y partial of, this is negative y over x squared plus y squared. Again, quotient rule. So the derivative of the top is negative 1 times the bottom left alone. So I'll go ahead and distribute that negative 1 to get minus x squared minus y squared minus the top left alone times, minus the top. Well, the top's already negative, so double negative gives us y times the y partial of the bottom, which is 2y. And you can see what's going to happen here. We get the same thing. So, yes, it is true that these two are equal. So, therefore, this implies that del f2 del x equals del f1 del y. So the cross partials condition is satisfied. So then they would like us, and by they I mean me, would like you to show that this vector field is not conservative. So ways that we could show that this vector field is not conservative is, well, one thing we could do, we could try to show that there isn't a potential function, right? That could be a little tricky. Or we could go ahead and try to do something that's maybe a little bit less daunting and do a line integral around a closed path. Because what do we know? So here's a fact. If a vector field f is conservative, then the circulation of f over some closed path C has to be 0. So let's go ahead and invent a closed path, C, and calculate this and see that it's not 0. Now, even if we got 0 as an answer, that doesn't prove that it's conservative, because you can have a vector field give you a 0 result for a line integral even if the vector field's not conservative over a closed path. But for conservative vector fields, every conservative vector field must have this property. So if we were to somehow find a path C and get a non-zero result, then this would force this assumption to be false, which would prove that our vector field F is not conservative. So let's go ahead and do that. Well, an easy closed path, the easiest, I think, closed path is a circle. And let's go ahead and just use the unit circle. So consider C, the unit circle, in R2. This can be parameterized by, well, let's just use the standard one. So R of t equals, we'll let x be cosine t, we'll let y be sine t, and we want the full thing, so we'll let t go over the range 0 to 2 pi. Okay, so that's a parameterization of the unit circle. Let's go ahead and calculate what this looks like. So as a reminder here, there's a reason why I also picked the unit circle. Notice in here we've got x squared plus y squared showing up. And remember, what is x squared plus y squared if we're using these like polar-like relationships? Well, in this case, on C, x squared plus y squared equals 1. So, fact, on C, our curve, x squared plus y squared equals 1. So, therefore, when we go ahead to do f of r of t for a line integral, we should get 1 in the bottom, negative sine t, cosine t. So this should just be negative sine t, cosine t. All right, let's go ahead and do this. So circulation of f over c is equal to the integral from 0 to 2 pi of our vector field, which is negative sine t, cosine t, once we do this composition. So I'm just using this right here. We are now to dot by the derivative. So the derivative here would be negative sine t, cosine t. Which is the exact same vector here. So this will give us sine squared of t plus cosine squared of t dt. But this is equal to 1. And the integral of 1 dt over 0 to 2 pi is just 2 pi, which is not 0. So this implies that f can't be conservative. Okay, now for the second part here. Is this a contradiction of Theorem 3? Let's go back and take a look at Theorem 3. So for Theorem 3, it says, let f be a vector field. Okay, we've got a vector field, so that's satisfied. On a simply connected domain, we didn't talk about this in our problem. If f satisfies the cross partials condition, which ours did, right? We satisfied that, then f is conservative. So here's an example of a vector field that's not defined on a simply connected domain. So look at our vector field here. Our vector field, f, is technically defined on the plane without the origin. I'm going to go ahead and write this as 0, 0 to emphasize it's the origin. Why can't the origin be here? Well, because at the origin we divide by 0 here and here. So this vector field only makes sense at all points in the plane except for the origin. And we did a line integral over the unit circle. And the unit circle contains the origin. So because our path of integration went around that point, the origin, that means we were treating the vector field as being defined on the punctured plane. So if we look at this, so there's the y-axis, x-axis. So basically we said, okay, we can't have that point in the middle. So we were really looking at this domain here. Everything except for that little center. Well, this is not simply connected because this is a hole. And our path of integration of the unit circle went around that singularity. In math, we call this a singularity or a pole. And it's because of this that we got a non-zero answer. So, does this contradict theorem 3? No, it is not a contradiction. Since f isn't defined on a simply connected domain. What's interesting is if we were to go ahead and consider this vector field as living somewhere else other than, so maybe we were thinking about the vector field living over here. So far away from the origin. If we were to then look at a line integral about a circle here, we actually would get 0, which is interesting.